Well, welcome to section SYM4. So we will start with a keynote lecture by Professor Bauer on advances in Ferronics.
Thank you very much, Mr. Chairman. I'm very grateful to the organizers for allowing me to be here. What you see here are not Pokemons, these are quasi-particles. If you want to collect them all, please go to the website of Professor Murakami's Chimera quasi-particle project that's listed here. Now, Mr. Magnon got a lot of attention already at this conference, but we didn't hear much about Ms. Ferron, so I will focus on her today. I would like to thank my team. Unfortunately, my teachers, Mehtat and Ping, have been promoted away, but there are two young postdocs, Juan and Yu Tian, to work with. Thierry Vallet is a guest professor in our group, and Aiko is our boss. I would like to acknowledge collaboration with experimentalists, especially Shianze Chen from Fudan University, and Ryo Iguchi and Kenichi Uchida from NIMS and the University of Tokyo. This is what I have for you today. I would like to start with a basic introduction into magnets and ferroelectrics, which are technologically extremely important materials, as most of you will know. Nature in condensed matter knows about two types of dipoles, magnetic dipoles and electric dipoles. Magnetic dipoles are generated by moving charges. They are called Amperian, and they generate magnetic stray fields. The elementary dipole of the electron is the Bohr magneton μb. The elementary electric dipole, which consists of two opposite charges, is the Bohr dipole, which is the product of the elementary charge and the Bohr radius. The electric field emitted by an electric dipole has the same form as the magnetic field emitted by a magnetic dipole. Now we are interested not in single dipoles, but in ensembles of many dipoles, and they interact with each other. Now electrons interact via the short range, but very strong exchange interaction, right? But the magnetic dipoles have also a magnetostatic or magnetodynamic type of interaction, which is actually much weaker than the exchange interaction, and usually not the reason for magnetism, for example. Now, electric dipoles do not have an exchange interaction, but they do have an electric dipole-dipole interaction, which is much stronger than that of the magnetic dipoles. And if you calculate this ratio, the electric dipole interaction is about 1,000 times larger than the magnetic dipole interaction, and it is very often the reason that ferroelectricity exists. So the interaction would like to organize and orient all these dipoles, but there's also the entropy, which prefers to have the disorder. Now, this can be captured in Landau's free energy formalism, and we see that the free energies look very similar for magnets and for ferroelectrics, with obvious small differences, such as the Zeeman versus the Stark interaction. So at high temperatures, the quadratic term is positive, all terms are positive, and we are finding that the free energy has a minimum at order parameter 0. Then we have a paraelectric or paramagnetic phase. At lower temperatures, however, we develop an inverse Camelback type of structure with two minima, which correspond to an ordered state where all the dipoles point either up or point down, like indicated here. Now, we know that magnets is a fascinating class of materials with many different examples, but magnetism here is usually dominated by exchange. Now, the class of ferroelectrics is maybe even richer than that of magnets, and I have just here a number of different interesting ones. The most common ones are the so-called displacive ferroelectrics, in which the transition to the ferroelectric state is as structural phase transition, it can be described by the condensation of a soft optical phonon. And I will concentrate on those. Now, many of the properties of these magnets and ferroelectrics are not ground state properties, but excited state properties. And the elementary excitations, the symbols, excitations of this electric order are quite important. So, in a ferromagnet, the symbols excitation is just a spin flip like that. Now, this causes exchange energy, and it reduces the total magnetization by twice the mu bar. Now, this is what we call a magnon. In the ferroelectric, we can also revert this electric dipole. Now, this costs elastic energy mainly, and dipolar energy. The total polarization by this excitation is reduced by minus 2p0. So everything is quite similar, isn't it? Now, these simple spin flips, they are not eigenstates. In order to have eigenstates, you can either diagonalize a Hamiltonian, or you can use some phenomenological approach. And we do this in magnetism by focusing on the Landau-Lifshitz equation, right? That is a continuum approximation. Now, the solution for a homogeneous system are plane waves, precessional plane waves with a quadratic dispersion, and a coherent type of motion, which is called the Kittel mode, which is in the gigahertz regime. If you want to understand ferroelectrics, we should solve the lattice dynamics of the charged particles. Again, this can be quite complicated, especially if you have important nonlinear terms. So also in this case, we can make a continuum approximation, and we then arrive at a neutron's equation, neutron-like equation, which goes by the name of Landau-Kalatnikov-Tani equation. The driving force here is not an effective magnetic field, but an effective electric field. And also this is a functional derivative of the free energy I introduced before. Now, the simple solution gives you again a quadratic dispersion, like indicated here. And this omega 0 is now in the terahertz regime. And we can calculate the dipole, which is associated with this excitation, by taking the derivative with respect to the electric field. Now, these excitations are small oscillations in this free energy potential, which is asymmetric. And this asymmetry reduces the polarization associated to these ferron excitations. Now, we can make wave packages out of these plane waves in magnets as well as in ferroelectrics. And these wave packages, they move, they are as a dip in the saturation polarization that moves with the group velocity. So that means in magnets, these magnons, they transport a spin or magnetization current. In ferroelectrics, the ferron, they transport polarization from A to B. Now, we can calculate the ground state properties and the currents by standard formula. And I should add that these ferrons and magnons are bosons and distributed according to Planck at equilibrium. Now, that was the elementary introduction. Let me now discuss some experiments which give evidence of these ferrons and also show that they can be pretty useful. Now, the first experiment is done by the group of Professor Zhu from Columbia University. They hit the sample with a femtosecond laser and observe intense terahertz radiation. Now, here you see this result in time domain and in frequency domain. After an initial strong excitation, there is a long coda which is monochromatic, which you can see best in the Fourier domain here. That the broad peak, The broad peak is the standard optical rectification, which is orders of magnitude larger than in conventional semiconductors, and there is a monochromatic peak with a quality factor which is much higher than most ferroelectrics and also almost all on many magnets. And I should add here that the material here is a van der Waals material. It's niobium oxyionide. Okay. Now, to have such a monochromatic peak of terahertz radiation is quite unique, and I would think that this has really applications. The next experiment from the same group is a focused laser excitation. So there's really a sort of a point excitation of our ferroelectric, and what they do is spatiotemporally observe the reflectivity as a function of time and function of position. So this first pattern here, we see on a very short time scale that things change from black to white, which basically gives you the oscillation frequency, and this is exactly the same we saw in the previous experiment. Here you see how, as a function of time, the signal expands. So it's like a stone you throw into the water and see that the water waves expand. Only here it's strongly asymmetric and with a little bit strange phase shape. Now, interesting here is the velocity of the wavefront, which is indicated here, which is much faster even than the sound velocity in these materials, and orders of magnitude than that what you expect for an optical phonon. Okay, so this is quite promising for the future, also for information transfer. Yeah, I should also say that this goes really very far. Now, how can we explain this? Now, what we have to take into account is not only in thin films like this, not only the LKT equation, but we have to couple it with the Maxwell equations. Now, this has been done by several groups, and you can calculate the dispersion. Now, here's a result for a thin film. Here's the result of a thin film, and in this mode here, we see that the lowest standing mode has a very strongly enhanced group velocity. Now, this mode, you can then plot it in a two-dimensional way. This has been done by Cheo et al. On the left side, you see the dispersion. On the right side, you see the temporal response, a snapshot after a few picoseconds, which looks very similar to what we see in the experiments. So basically, we can explain this acceleration of the signal in terms of dipole-dipole interactions, electrodynamic interactions. Next experiment, so this was clearly a diffuse signal. We saw that the signal ballistically is transported in the film. But usually the transport of magnons and also ferrons is diffuse. Now, to study this, the group of Xianzi Chen has done non-local experiments in which on a ferrostandard ferroelectric, they put on two electric contacts of a metallic ferromagnet. Now, driving a current through one of these contacts gives you a voltage on the other contact. This is a non-local result. So you drive on the left side, you see a signal on the other side. So some information is then going through this ferroelectric material and is detected on the other side. Now, this signal is strongest when the magnetization of these magnetic strips is normal to the interface. We see that the signal, we can sort of look at the distance dependence. So this linear signal goes like 10, 20 type of micrometers. And yeah, other people have already shown that this is not a direct electromagnetic type of reaction. And if you do the same experiment on non-ferroelectric materials, the signals are observable, but orders of magnitude smaller. So what is happening here? Now, that is maybe a bit specific, but it is due to the spin Hall effect in the ferromagnetic metal. So the spin Hall effect generates transverse spin currents, and these spin currents must be polarized along the magnetization, which we assume to be normal. Now, the conductivity, so upspin and downspin, is different in a ferromagnet, so these spin currents are coupled to the charge, and they generate a charge polarization accumulation at the edges of this material. Now, these generate fluctuating electric fields. They inject ferrons into the ferroelectric, which then diffuses to the other side where the reciprocal process occurs, like indicated here. Now, simple symmetry arguments would convince you that the linear response, which is proportional to the applied current in the injector, cannot depend on the direction of the magnetization, so it must go like mz squared, and it cannot depend on the polarization. If you want to see effects of the ferroelectricity, you have to go to the next higher term, which is the cubic one here. The cubic one here, this one. So that means that the sign should change if you change the magnetization direction, and the sign should change if you flip the polarization. And this is beautifully confirmed in the experiments. And this nonlinear signal even goes up to 100 micrometers, so it's very far distance. Okay, next I would like to discuss the thermoelectrics of these materials, especially ferron dielectric Peltier effect. Now, what happens if you try to do transport experiments on a ferroelectric condenser, which is an insulator, right? You would say, okay, there are no charge currents. But polarization of ferron currents can flow under either a gradient of the electric field or the gradient of the temperature. Now, the polarization and the heat current are related by a 2x2 Unsager type of resistance, which characterizes here the Seebeck coefficient and the Peltier coefficient. So now, how can you test that? What is this polarization current? I try to indicate it here. It's a real transport current of electric polarization. It does not move under constant electric field. You need a gradient of the electric field to move these dipoles. And the heat, if there's a Peltier effect, the heat current should be proportional then to the gradient of the electric field as well. But the heat generation then is proportional to the divergence of the heat current, right? The heat current itself cannot be seen. Now, how can you check this? Now, you can do this by look in thermography on ferroelectric materials. So this is just a method to measure temperatures as a function of time and as a function of space. The sample here would be this ferroelectric. Is this ferroelectric here, right, which then is sort of connected to probes, and you can from above look how the temperature develops. Now here's a result from the Fudan group, and this is the experiment I showed before, in which this one here is sort of the injector, and these two are the detectors. Now here we drive a current through this line here, and then the thermography measures the temperature changes here. And we see that it gets cooler on both sides of the edges with the same sign as actually we would expect. We also see that it's extremely localized. Again, it agrees with the spin Hall effect type of interpretation. Okay. Now there is another experiment which was carried out at NIMS in Japan. Now also these look now at a ferroelectric condenser, and they apply an electric field over it. But this electric field is constant. A constant field cannot drive a polarization current. Nevertheless, they see results. First of all, they see the so-called electrocaloric effect, which is very well known. It's an equilibrium effect, which is entropic. It means that you have you apply a constant electric field, and the temperature of the system changes. It becomes hotter or cooler. Now, this is exactly what they see here. Now, this electric field in this experiment changes sign. It's time-dependent perturbation. It changes time at frequency omega. Now, the direction of the electric field is unimportant in this case. So that means that the signal has a frequency 2 omega. Again, this one here is well known, so there's no discussions about that. This one is new. It's a Peltier effect, which occurs at the edges. If you look at the phase, you see that one edge is getting hotter and the other is getting colder, which is quite different from the Ferron-Peltier effect I showed before. So what is happening here? Now, it turns out that a long time ago, there has already been a theory of thermoelectric effects in electric insulators by Maval. So the 2x2 Unsager relation is exactly the same as in metals, but this JC, this AC cannot be a constant one, right? Because it's an insulator. So what is this JC? Now, this JC is a so-called shift or displacement current, and I try to indicate it here. So if you have an electric field, then it reorients all the dipoles. Now, this is a transient effect. If all the dipoles are oriented, it stops. So these experiments have zero result if you go to frequency 0. But in principle, to this current, displacement current, there should also be a heat current if it's somehow coupled in an incoherent way to some heat path. But the microscopic theory is not clear. Now here's another hint what could be happened, because as a function of temperature, we see a critical enhancement of the signals at the critical temperature Tc. Now this is again not very surprising here for the electrocaloric effect, because this is just a susceptibility which diverges at the phase transition. But we also see a strong enhancement of the transport signal, which is completely different physics. And we do not have a good explanation for that. So here are the problems. First of all, this Peltier coefficient in insulators is orders of magnitude larger than that what we know from conventional metals. So it's 100 volt, which is huge. We have no idea what the microscopic mechanism is at this time. One of the reasons could be simply that we are using linear response theory, which is actually not allowed if we have these large amplitude fluctuations where the order parameter flips from one to the other side. So, and we can ask, can we apply a thing like that to something useful? Now, one direction we are thinking about is maybe we have domain walls which are operative here. Now, domain walls are, of course, well studied in magnets and also used in devices such as the racetrack memory. Juan here then asks the question, okay, can we do similar things? Can we drive domain walls also by a polarization current? And also with support with Professor Yen here, he was able to solve this problem. And he found, indeed, you can drive domain walls. And the domain wall velocity can actually be very fast. So this is quite promising. But what has this to do with the dielectric Peltier effect? Now, we can look. We now know that a current can move domain walls, right? Yes. Then oppositely, it means that, a current, a heat current, a Ferron current, which can generated by gradient of the temperature, can move the domain walls. The reciprocal effect is that moving domain walls generate heat current. And now, if you look what happens here, then we have these type of domain wall structures when we flip the magnetization, and they move in this direction and in this direction when the electric field is flipping. And these drive heat currents in one direction, and we get divergences at the edges, and that may be what the experiments observe. Okay, then I'm coming to my conclusion. Please, you can read it yourself. Thank you very much for your attention.
Thank you. So, time for questions.
Thank you for the talk. I will ask extremely stupid questions because I don't know anything. But How is this ferron related to optical phonons? Maybe it's some kind of can be represented as a superposition of phonon modes. That's the first question. Second question: if your electric field is not just linearly dependent on doesn't have just gradient, but second derivative, would you expect then to be have a real polarization charge? Because your polarization will be different. Polarization will have gradient, then there will be a real charge?
Yes. Okay, the first question is indeed sort of among these different ferroelectrics, indeed the displacive ones are the most common. So there the phase transition occurs by so-called soft optical phonons, which sort of goes from a finite energy goes to zero. In this case, the amplitude becomes large and you get the structural phase transition. Now, below the phase transition, you have something which corresponds to this optical phonon, and that is what we call a ferron. Now, we call it a ferron because it has many properties which have been up to now completely neglected. For example, each ferron carries an electric dipole, it carries polarization, just like a magnon carries spin. Moreover, it oscillates in a strongly nonlinear type of potential, which, if you just drive it a little bit, gives you these exciting effects, as measured, for example, in the terahertz generation. And indeed, the polarization, if you move polarization, it will basically, it will give you charges. It charges your capacitor, and this can be measured simply by voltage. Yes.
Okay, maybe we have one short question. Okay.
So, Gary, is it possible to have a ferroelectrical metal?
Pardon me?
Is it possible to have a ferroelectrical metal?
Yes, this is possible, and there's active research going on that. There are strongly correlated materials with weak screening where something is seen, but much more interesting, in my opinion, are van der Waals materials, in which the polarization is normal to the layers, while the electrons flow in the layers, because then the free electrons cannot screen this perpendicular polarization. So rhombohedral graphene is one of these materials, fascinating materials, where ferroelectricity is combined with electric conductivity. That's a very interesting system, yes?
Okay, in the interest of time, let's thank Professor Bauer for a wonderful talk. Thank you.
Thank you.
So let's now move on to the second talk.